we're going to look at this thing called the primitive function. So I guess the question is, if we know the equation of the tangent, how do we find the equation of the original curve? So it's going back the other way. Normally we've got the curve, we want to find the equation of the tangent. Okay, well, in other words, we know the derivative. Now, that derivative, say it's, again, we're talking about polynomials, so it's x to the power of n. Well, we know that when we differentiated a polynomial, we subtracted one from the power. So logically, if we want to go back the other way, we'll add one to the power. Also, when we differentiated, we multiplied by the original power. Here we're going to divide, but not divide by the original power, it would have to be the new power. Because if we differentiate this x to the power of n plus 1 on n plus 1, I've got to end up with x to the n. So I would bring that power of n plus 1 out the front, it would cancel with the fraction, subtract 1 from the power, and we get x to the n. So if we know the derivative is 3x to the power of 4, then the original curve that it came from, add 1 to the power over that new power, 3x to the 5 on 5. But we need to add a constant in. Because the other thing we know about differentiating is when we differentiate a constant, we get 0. So how do we know there wasn't a constant there? Now, unless they give us more information, best I can do is say, well, plus some constant. I mean, it might turn out that constant is 0, but just some constant number there. Just like when we were differentiating it, we do it term by term, same when we're going back the other way. So add 1 to the power over the power, we'll get 6x to the 4 over 4, then 5x cubed over 3, x squared over 2. Well, the 2 becomes 2x over 1, but obviously we're not going to write it over 1. And we have a constant as well. That first fraction simplifies, so we'll get 3 over 2 for that one. Now, whether you leave the pronumeral on the top of the fraction, or whether you just write a fraction as the coefficient, it's really up to you how you prefer to write those down. All right, so let's go and solve the problem then. What is the original curve? We know it passes through the point 1, 1, and it has a gradient function of 2x plus 3. A gradient function. So the function that allows us to find the gradient, that's just a fancy way of saying the first derivative. I mean, that's the function that allows us to find the gradient. So they're telling us that that first derivative is 2x plus 3. Now notice the difference in my notation here. This time I've decided to use dy dx because I'm going to end up with an equation of curve which I'm probably going to write as y equals. So I sort of match the question. Add 1 to the power over the power. Well, the 2x will become 2x squared over 2, but the 2 over 2 I've already simplified down. The 3 becomes 3x plus some constant, but now we have an additional piece of information, and that is that it goes through 1, 1. You see, if I was just to draw the primitive function of x squared plus 3x plus a constant, I get a whole series of curves, or an infinite number for that matter, for whatever the constant is. We're saying which particular one of those will go through 1, 1. All we've got to do is substitute 1, 1 in, and we can work out what the constant is. So we know that when x equals 1, y equals 1, so our constant is -3. Thus, the equation of our original curve, it was a parabola, it was x squared plus 3x minus 3. Okay, and that will finish us for the year.